My name is Jed Murdoch. Welcome to Module 3 on Population Viability Analysis. Population viability analysis is a very useful and helpful tool when it comes to managing populations because it allows us to estimate or to project how a population will behave in the future. So in this module, we will introduce you to the basic idea of population viability analysis. We'll walk you through a number of the steps required in order to do this and why it might be helpful for managing populations. Oftentimes, PVAs are used for populations of rare, threatened, or endangered species, but in other circumstances, they may be used for more common species or any species that may be requiring management. So with that said, let's begin. Population biologists are oftentimes concerned with answering a fundamental basic question about populations. How small can a population be and still be persistent into the future? It's a basic question we oftentimes grapple with. So imagine a situation involving a very rare species, like, let's say, the Iberian lynx. The Iberian lynx is perhaps one of the rarest cats in the world. There's only about 100 or so remaining in the wild, most of them in Spain, but some may also be in Portugal as well. We know that there are only about 100 individuals left, and this population is declining. So we really are concerned with managing this population and trying to estimate whether that population will be viable, whether it will persist at some point in the future. That may be in 5 years' time, in 10 years' time, in 50 years' time, maybe even beyond 50 years. So we're interested in trying to get at that question, given what we know about the population, given what we know about its current state. Population viability analysis, which is sometimes referred to as a PVA for short, is really a tool that allows us to do that. And really what we're trying to do is estimate not only whether a population will persist at some point in the future, but really what the probability of persistence is, or the probability, you could say the converse, the probability of extinction. And when we have that information, it gives us the capacity to make some judgments and to make some decisions about how we manage that population. So PVAs have been conducted on a variety of different species in a whole variety of different situations. We've had PVAs conducted on African elephants, on ocelots, on koalas here in North America, on bighorn sheep. Perhaps one of the earliest examples involved a PVA that examined a grizzly bear population and really found that about 50 bears would be needed in this particular population to ensure a 95% chance of surviving in about 100 years' time. So PVA is a very powerful tool. It's a good analytical tool that gives us some very vital information that helps our decision-making processes about managing a population. But think for a moment, what sorts of information would you need to project into the future? What information would you need about this current population? Certainly, as a starting point, you need to know something about the size of the population. We need to know what starting point to begin with. How large is that population? In the case of lynx, we have a starting population of 100 individuals. That's where we start, and from there we project forward. We also need to know something about population trend. We need to know something about population growth, how that population is changing, let's say, from one year to the next. Population growth obviously can be positive, but in some cases it can also be negative, and we find in some circumstances population growth can be neutral. In other words, the population is stable and doesn't change from one year to the next. But by and large, over time, population rates change. So not only do we need to know some measure of population trend, but we need to know how much variability there is in that population trend. So we need to know something about how it changes over time. With these two key pieces of information, a starting point, a good starting population, and some measure of trend then, we can project into the future and try to make some judgment about whether a population will be persisting or whether it will go extinct, and in fact what the probability of extinction and what the probability of persistence in fact might be. So in order to do that, we need to cover a few basics about population growth, which we'll do in just a couple of moments. The population growth rate is a function of the number of births and deaths in a population, and oftentimes we refer to that by this value here called R. And R is the geometric rate of increase. And we basically define it by the births and the deaths. It's births minus deaths, and we're not using raw values here. We're actually using per capita rates. So those are per individual rates. In the case of births, for example, that's the number of births per individual per unit of time. So births minus deaths then will give us this value for R. And how do we interpret R? When R is a positive value, we have the population increasing, right? We have more births than deaths. If R is a zero value, what would you guess? The population here would balance itself out. We'd have a stable population. And if it's negative then, we would have a decreasing or a population on a negative trajectory here. So let's consider our population of links. So we'll define n here as our number of links, and we'll call number of links at time t our starting point. So that's right now. That's how many links we have right now. And we're interested in estimating how many links we have at time t plus 1. And that is time one step in the future. So we may be dealing with years, for example. When we're dealing with years, t plus 1 is 1 year from now. And we can define that based on this equation here. And that's simply our population now plus r times our population now, which really gives us a measure of whether the population has grown or declined. It gives us a measure of whether we've gained or lost individuals. And again, we're adding that to what we have at present. So we can then take this value here, nt, and we can do a little algebra and we can pull that out. We can factor it out of our equation, and now we've got a new equation, which is simply our estimated population in 1 year's time as being 1 plus r times our current population. I'm going to star this equation because we'll come back to it in just a moment. So this value of 1 plus r, we actually give a new term, and we call that thing lambda. So lambda is referred to as the finite rate of increase, and we interpret it similarly to r, except because it's 1 plus r, when we have a lambda value that's greater than 1, our population is increasing. If our lambda value now is 1, our population is stable, not changing. And if our lambda value is less than 1, our population then, again, is on a downward trajectory. It's declining. So if we come back to our original equation for nt plus 1, what we expect our population to be like one time step into the future. I starred this before, so you might recall. We have the value 1 plus r times nt gives us that value. And so we can substitute in here our lambda for our 1 plus r term. So we're multiplying now lambda times nt to get at this value. And we can rearrange this formula a little bit by kind of solving for lambda. And when we do that, if we're interested in our finite rate of growth, which we will be for a PVA, we then have the equation here. And basically what's that's saying is the population in the future, let's say next year, is a certain value. Then we divide that by our value at our starting point to arrive at a lambda. So let's put some numbers at that. Let's say that our current population is 60, and we know next year that our population increases to 72. So the question is, what is our lambda value here? What's our growth rate for this population? Well, it's simply 72, our population one time step ahead, divided by our current population. And if I've done the math correctly, that should be a value of 1.2. Now we can think of this in different terms as well. If we know what the value of lambda is for our population, and we multiply that by our population, we then arrive at what we expect our population to be one time step in the future. That's what we'd expect to be nt plus 1, 72 individuals.